I'm going to take a step back just for a moment, because yesterday we finished with molarity, other than the review for the quiz, looking at acids and bases, both ionic and covalent bases, and what they produce. An acid and a ionic base produces water and a salt. An acid and a covalent base produces ions, which are basically the base plus a hydrogen, and then the remainder of the acid. Those are the two ions. Then we moved into a discussion on molarity, and I mentioned that molarity is a measure of concentration. Molarity is not the only way to measure concentration. Concentration is just material over volume in whatever units they happen to be. Molarity is specifically moles per liter. Okay? So whenever you have a quantity of a substance in a volume space, you can figure out the molarity by saying how many moles are in any given liter of that material. So you're going to be dividing the moles of material by the volume of the material in liters. Sometimes you're not given moles, right? Sometimes you're given grams. And we know now that in order to get moles from grams, you take the mass in grams, divide it by the molar mass, and that'll give you the number of moles. Okay, so molarity equals moles per liter moles is equal to mass divided by the molar mass. And so we can rewrite this as mass divided by its molar mass, all divided by its volume. And we finished yesterday by doing by doing the examples 9-4. So on your own 9-7, encourage you to do that on your own, but it's basically the same thing moving forward. If you look at the questions for the on your own section there, they give you they give you a certain number of moles. In addition 3, it's 0.21 moles of HCl in 0.346 liters. All you're going to do is divide 0.21 by 0.346. In the second one, it's grams of sulfuric acid dissolved in water to make 6.8 liters, right? So I'm given the grams of sulfuric acid. I'm going to have to compute the molar mass of sulfuric acid. From that, I take the mass divided by the molar mass to get the moles, take that number of moles and divide it by 6.8 liters. And then lastly, the grams of potassium hydroxide. That's our base, right? Potassium hydroxide is a base, so we're going to take 5.55 grams of potassium hydroxide divided by the molar mass of potassium hydroxide, which gives us the moles of potassium hydroxide. Divide that by 0.125. It's going to be 0.125 because your units here are milliliters, right? If you go ahead and convert it to liters from the very get-go, then you have the correct units, moles per liter. So if it's given to you in milliliters, move the decimal 3 places to the left, and your units change from milli to the base unit. So milliliters becomes liters if you move the decimal place 3 places to the left. All right. Now, one of the very practical things you can use in order to, for example, make solutions, and we're going to see that in a moment. A chemist needs to make a solution with a certain molarity, but they don't have that molarity. They've got another molarity. They've got a solution that's not the same percentage. Remember yesterday we talked about the works, which is basically a diluted muriatic acid. And muriatic acid is basically water and hydrochloric acid. So muriatic is about 30% hydrochloric acid and 70% water. But the works is about 97% water and 3% hydrochloric acid. It's the same stuff, just in different proportions, a different concentration. Pure muriatic acid from the hardware store is much stronger, much more caustic than the works. The works you use in your bathroom, kitchen, wherever you're working, you get it on your hands, not so worried about it. Muriatic acid, you drip some on you, you have a burn, okay? And even muriatic acid is at a 30% HCl, 70% water, because getting even more concentrated than that, it becomes more and more caustic, more and more harmful to you, more and more dangerous to deal with. So, dilution is basically adding water to something in order to decrease its concentration. We mentioned yesterday about taking orange juice. And when you take the orange juice, you take the oranges off the trees, you squeeze them, you get orange juice. You evaporate out the water, or you remove the water through a process, and you're left with concentrated orange juice. It comes to you in a can, usually frozen. That's a concentrate. If you think about it, when you take that orange concentrate in the pitcher and you add water to it, yes, you're re-adding the water that used to be there. What you're actually doing also is diluting the concentrate, right? Anybody in here ever take those formulas, like the side of the can says, put the contents in a pitcher and add 3 cans of water. But you know, that's just not strong enough, right? So what do? You only add 2 cans or maybe 1.5 cans. And so you get like the super concentrated orange juice. Oh, this is really thick. This is really powerful tasting stuff, you know? Or you can add extra water, more than it calls for, and you end up with something that tastes more like a punch rather than orange juice. Because really what we're used to is a certain concentration of the citric acid, you know, and based upon the fruit, different other chemicals that give us that little bit of a acidic taste in our mouth. I mean, that's what we're actually looking for and longing for, and our bodies are craving some of the vitamins and other things that are in the orange juice. So when we take something and it has a certain concentration and we add additional water to it, what we're doing is diluting it. You probably use that term in the vernacular anyway, so you're used to this idea of dilution. But there's a really neat formula here, our dilution equation. And it looks like this. M1 V1 equals M2 V2. Now, it may look like a physics problem talking about momentum, but it's not, okay? This is not mass times velocity. This is molarity times volume. So let's think of it as 2 different states. And again, not as in Ohio and New York, but as in something before we do something and something after we do something. Let's go ahead and imagine, if we can, we have a beaker. And this is the same beaker, but in different time, okay? This is where I start from, and this is where I end at. Maybe in chemistry, we might do something like this. This becomes this. Let's say that in this beaker, I have a certain amount of fluid, and I add to it a certain amount of salts that gives me a certain molarity, okay? I have a certain amount of this solid that's mixed up into this liquid, which will give me a certain molarity here. And so I've got a certain molarity, and I also have a certain volume. How much of it do I have? So molarity, and if I use the number 1, what that means is molarity in my first state and the volume in the first state. If then, after I have this certain molarity that takes up a certain volume, and I run more water into it, if I add water, and I add water into this, and I have a certain molarity, I don't add any more salts. So the amount of salts that I put in there doesn't change. However, I add water, and I increase the volume. I have a new molarity and a new volume, okay? An initial molarity, which again, conceptually, the molarity is just the amount of stuff I have of whatever I've dissolved into there. How much do I have over a given volume? If I put, let's say, if I have 1 mole, and my volume here is 1/10 of a liter, then my molarity would be 1 divided by 1/10 would be 10, right? A 10 molar. I have a 10 molarity because I have 1 mole in 0.1 liters. But let's say over here, I add enough water to increase the volume to go from being 0.1 liters to being a full 1 liter. I've got 10 times as much stuff, 10 times as much volume of stuff. But I haven't added any more salt. So if I have 1 mole of salt in here, and all I do is add water, how much salt do I have in here? 1 mole still, right? I still have 1 mole. However, my volume has changed. So my molarity on this side would be 1 mole, because I haven't added or taken away any of that stuff that's dissolved. But my volume now is 1 liter, and my molarity here is equal to 1. And you see that the relationship between the molarity and the volume is an inverse relationship. As I add more water, my concentration goes down. So more water, less concentration. Let's say that this is salt water. If If I take a drink from this side, it's going to be very salty. If I go ahead and add 9 or 10 times as much, don't add, I had 9 times as much, right, because I already have 1. But I had 9 times then, so I add a lot more water and I take a drink, it should be intuitive that it's going to be less salty. But there's still the same amount of salt as I started with. I haven't changed the amount of salt. All I've changed is how much fluid that salt is in. So the way this equation works is, if I know at least 3 of the 4 variables, I can solve for the unknown. If I know how much stuff I had in moles at a given volume, and I know how many moles in a given volume I end with, then I can solve, whichever one I don't know I can solve for. Like if this is A, B, C, and D, I can solve for any variable if I have the other 3, because I can rearrange the equation. Now, remember, we're using just cross multiplication. If I take this equation, and this might seem simplistic, but let me run through it for you, just to make sure we all have it. If I'm looking for the initial molarity, what's it going to be? Well, it's going to result, this is going to rearrange to be M2V2 over V1. What's that saying? If I'm looking for my initial molarity, I can solve that if I know my final molarity, my final volume, and my initial volume, because it's going to be equal. Now volume 1 is the same thing. Molarity 2, volume 2 over molarity 1. Molarity 2 is equal to molarity 1, volume 1 over volume 2. And volume 2 is molarity 1, volume 1 over molarity 2. So these are the 3 or 4 different ways we can rearrange this formula and solve for whatever unknown we have if we're given the other 3. Look at example 9.5, and we'll leave that on the right side of the board. Looking at example 9.5, it says a chemist wants to dilute 12 molar HCl to make 500 milliliters of 3.5 molar. How will he do this? Okay, now let's think about this for a minute. We start with a 12 molar hydrochloric acid. What variable am I going to assign to the 12 molar hydrochloric acid? M1, my molarity 1. My initial molarity is 12 molar hydrochloric acid. What is my 500 milliliters? The chemist wants to dilute 12 molar to make 500 milliliter. So this is my ending volume. I want to make this much. So that's going to be my end state. I start with this state, molarity. I end with this volume. That's my V2. And it says to make 500 milliliters of 3.5 molar hydrochloric acid. So this is going to be my ending molarity, right? So I have a 12 molar hydrochloric acid, and I want to make 500 milliliters of 3.5 molar hydrochloric acid. So this is my beginning, this is my end. What do I lack? I've got M1, I don't have V1, right? So if I'm given my initial molarity, I'm given my final volume and my final molarity, with the dilution equation, I can compute how much do I need to start with, volume-wise. I'm going to go ahead and write this in a standard format for liters. So I'm going to put 0.500 liters, right? Take the decimal, move it 3 to the left, lose the milli, because I know I'm ultimately going to divide by liters. So we're going to go ahead and solve for the initial volume. M1 V1 equals M2 V2. Solving for V1, I'm going to do this again, not assuming most of you don't know how to do it, but just so you have it, to make sure, confirm. How did I come up with this? Well, the shortcut is sliding diagonally across the equal sign, right? I'm looking for this, so I slide a numerator to the denominator. Let me go through how it would look longhand. I have M1 V1 equals M2 V2. I'm trying to get V1 all by itself, so I need to get rid of whatever is also with it on that side of the equal sign. I want V1 by itself, so if I divide both sides by M1, M1 cancels M1, I'm left with V1 equals M2 V2 over M1. Okay. So now that we've rearranged the formula to solve for initial volume, we'll plug in what we know. V1 equals M1, 12.0, excuse me. V1 equals M2. M2 is 3.5 molar. V2 is 0.500 liters. M1 is 12 molar. Okay. Check our units. We have molarity, liters, molarity. What are my units going to be in my answer? Well, molars cancels molars, and I'm left with liters. So my answer is going to be in liters, so I know my setup is right. He did it here in milliliters. Since we're doing it in liters, we can then, let's see, so it would be, which is 0.150 liters. So I take 3.5, I multiply it by half, which would give me 1.75, and then divide that by 12. And it gives me 0.150 liters. Now, what does this mean in real life? What this chemist would do was take the 12 molar hydrochloric acid, take a beaker, oh, they're all locked up, okay? So you have a beaker, take your 12 molar hydrochloric acid and pour out 1/2 of a liter, okay? Take 1/2 of a liter of the 12 molar hydrochloric acid. Then take that hydrochloric acid and put it in a container so that he would add water, or she would add water, until the total volume was half a liter. Okay? So you take 0.15 liters hydrochloric acid. I said that backwards before, didn't I? Let me start all over again. I'll make sure I get it right. What this person is going to do is take, okay, we're going to take the 12 molar hydrochloric acid and pour out 0.150 liters of it into a container. So 12 molar at 0.15 liters volume. Then we're going to add water to it until we have a total volume of 1/2 of a liter. So we're going to add 0.35 liters. See that? We've got 0.15 liters of 12 molar hydrochloric acid. If we add 0.35 liters of water to that, we will have a total of 0.5 liters of solution. And when we do that, when we dilute that 12 molar by adding 0.35 liters of water to give us 0.5 liters of solution, that solution will have a 3.5 molarity. Looking for someone to be excited about this, and I'm not feeling it. Okay. Let's go ahead and look at a second problem. Hopefully, for those of you writing this down, do you have it? It's in the book, but this is you know, for what it's worth, my working through it. Yes, sir.
I'm confused on how you decide. I'm confused on how you decide like what M1 is and P1 and M2 is.
It's straight from the problem. Remember, anything over here, the ones, if it's subbed 1, that doesn't mean like in chemistry where it's 1M and 1V or 2Ms and 2Vs. This is talking about its state. M1V1, you might want to put it this way. If you think of the 1 as being molarity initial and volume initial, its starting point, where it starts from, equals molarity final times volume final. Okay? Does that help you understand that? So your starting molarity and your starting volume is going to equal your final molarity times your final volume. So in this problem we just did, we were given the molarity of our hydrochloric acid to begin with, and we were told how much of it we wanted to make by volume and what molarity we wanted to make. And so then we just needed to figure out how much of the initial stuff we needed to pour into the beaker to fill up to the volume we needed. So a chemist, this is the second part of example 9.5, third edition. A chemist takes 2.5 liters. Okay. A chemist takes, so we have a pretty good idea this is our initial state, right? So I'm going to go ahead and just add this to our format up here. Initially is M1, V1. And then we also are going to have a final state, which is going to be our molarity in the second state and our volume in the second state. So let's just start with that on the board and then read the problem and fill in what we're given. A chemist takes 2.5 liters, molarity volume, 2.5 liters of 5.6 molar of sodium hydroxide and dilutes it, right? We're going to the second state now, final state, dilutes it with enough water to make 10 liters. So my second volume, I'm going to end at 10 liters. What is the new concentration of the sodium hydroxide? Okay. So we get all of that from the word problem. We're taking 5.6 molar solution and we're taking 2.5 liters of it. We're then going to add water to the 2.5 liters until we have 10 liters. How much water am I going to add? I start with a 2.5 liter. I finish with a 10 liter. I'm going to be adding 7.5 liters. To go from 2.5 to 10, I need to add 7.5. Okay? That's something for you to know and understand, but that's not what the problem is asking. I don't really need to know how much water am I going to add for this problem. Other ones we will. Let's say, for example, that we were told we wanted a certain molarity. What volume would we need? Like the last problem. Okay? We would say we need a particular volume. Well, we're going to add the difference to get to that volume. But right now we're looking at the second concentration. What is the concentration of the sodium hydroxide after those 7.5 liters of water are added to it? Again, straightforward formula. M1V1 is equal to M2V2. And we're going to rearrange it so that we're looking for M2. We get M2 alone on one side of the equal sign. What this is going to rearrange to is that M2 is equal to M1V1 divided by V2. How did I do that? Shortcut, I took this and I slid it across the equal sign and to the opposite. So I took it from the numerator to the denominator. That's a short way. The long way, M1V1 equals M2V2. I'm looking for, I want to have M2 alone, so I need to divide by V2. I have to do it to both sides, and I'm left with M2, since these cancel. M2 is equal to M1V1 over V2. So, M2 is M1 V1 over V2, which is equal to, go back to what I've been given. M1 is 5.6 molar. V1 is 2.5 liters. V2, 10 liters. Liters cancels liters. I'm left with molarity. And my final molarity then, 1.4 molar. What does that mean? 1.4 molar. If my final solution has a 1.4 molarity, what does that mean? So in the final solution, when I have my 10 liters, if I were to take those 10 liters and I were to, make sure it's thoroughly mixed, it was a fully homogeneous mixture, and I were to take 1 liter away, okay? Think about this. If I took 1 liter of my final product, my final solution, I took 1 liter of it and I boiled it somehow, and I was able to remove all of the water from it, okay? What would be left behind? If I take my final solution, I take 1 liter of it, and I somehow remove all of the water, what would be left behind? Correct, 1.4 moles of sodium hydroxide. Okay? Because what this is saying is for every liter of solution, inside of it is dissolved 1.4 moles of sodium hydroxide. Okay? And this is the important concept we're going to get to in titration, is because we're going to start talking about volumes of molarities. If I said to you, I need to get 1.4 moles of sodium hydroxide in an aqueous solution, you would say, I can do that for you because I have a 1.4 molar sodium hydroxide, and you need 1.4 moles. Well, if you measure out 1 liter, in that 1 liter, there are 1.4 moles ready to go into reaction. Let's suppose we had a stoichiometric equation up here that said I needed to have 2 moles. Okay? If I needed 2 moles to react, and I have a 1.4 molar solution, you can figure out, well, if I need 2 moles, and I have a 1.4 moles per liter, then I can figure out how much do I need to get 2 moles. If I told you you needed to get 2 moles of sodium chloride for a reaction, and you had salt over here, you would go to the balance, you would figure out the molar mass of sodium chloride, and you would measure out the mass that would give you 2 moles, right? And if I said take that and dissolve it in water, you'd take your 2 moles and you just add water to it and dissolve it, and you'd say, I'd say, how much sodium chloride do you have? You'd say, we still have 2 moles. I had 2 moles, I added water to it, I still have 2 moles. I haven't changed how much sodium chloride I have, I've just put it in an aqueous solution. Over here I said, okay, let's suppose that we have sodium chloride in a 1.5 molar solution, meaning I already have salt water. And the salt water is made so that every liter has 1.4 moles. Now I'm doing a reaction. Rather than giving you dry salt that you add water to, I'm giving you it already in solution. The question is, how many liters do you need in order to have 2 moles? Because you want 2 moles for the reaction. How much do you need? You would be able to figure out how many moles you would have. If you know how many liters, you could actually then measure out the volume and say, rather than looking for so many grams of sodium chloride, I'm looking for so many liters of sodium chloride. Why? Because within that, I know I have a certain number of moles of sodium chloride. Okay. You could see if this was a lot more concentrated, let's say that this was a 2.8 molar solution, I would need half as much of it to get the same number of moles, right? If I have something that has 5 moles per liter and I have something that has 10 moles per liter, I know that whenever I actually try to use it in a reaction, I'm going to need twice as much of the less concentrated than of the higher concentrated. I'll do what I can to help you. I mean, I can't do much if your heads are down, your eyes are closed, you're not paying attention, and you don't really look like you care to. I can't do much more for you. Like I said, told somebody yesterday, I can help you as long as your attitude's right, but once your attitude goes bad, you're on your own, okay? So, let me ask you then, any questions on the dilution equation? Because the next section on the importance in chemistry is, right now I can't tell whether it's so simple you've got it, you don't want to pay attention, or you don't care, and you don't want to pay attention. I'm not saying everybody's not paying attention, I'm just saying as a class. Right now, there's a lot of nonverbal feedback up here that's telling me, yeah, whatever. Until, of course, you go for a week without talking about it, and that's like, I don't remember how to do this. And then they'll be, Mr. Baker, can you help me at the last minute? And I'll go, sure, because that's what I do, to a degree. If you're in third edition, let's go ahead and, actually, let's go ahead and not go there. Let's do the on your own together, since either A, you don't care, or B, it's so simple, you don't even need to go over it. And let's see which one it is. Leave that? Yeah, I'll leave that on the board. Why not? 9.8. A chemist needs to make 500 milliliters of a 2.5 molar solution of sulfuric acid. So they're going to make 500 milliliters of a 2.5 molar sulfuric acid. Looking on the shelves, she finds a bottle of 10 molar sulfuric acid. She finds 10 molar sulfuric acid. How can the desired solution be made? How will she make it? She needs to make 500 milliliters of a 2.5 molar, and she finds on her shelf that she has a 10 molar solution already. How will she make half a liter of 2.5 molar? Yes, I'll reread the question. A chemist needs to make 500 milliliters of a 2.5 molar solution. And that's a solution of sulfuric acid. Looking on the shelves, she finds a bottle of 10 molar sulfuric acid. How can the desired solution be made? How can she make this if she has this? Because she's not going to have a bottle of pure sulfuric acid because it's going to be dangerous for her and for anybody else that it might spill on, right? So we have it in a manageable, safe concentration, relatively safe concentration. So it's not pure. We have a relatively safe concentration, but she needs to make a certain concentration, a certain volume of a certain concentration. And she has this as her raw material, 10 molar sulfuric acid. And just get a few steps ahead of me, and then I'll start into working with you. Sorry, we'll go back to closing the door and get warm again. You guys are so distractible. It's incredible. I'm just glad that doesn't have a window on it, because here nobody gets in that corner where you can look through, but here people be going all the time, and I'd lose you for 20 minutes. You go, did we even have class today? Oh yeah, up until the point where that 6th grader jumped up and saw their head, and then I lost it after that. Maybe start doing class in 30-second segments, so like everything's a commercial. 30 seconds, I'm done. I got to go over here and do this one again. I'll come back to that commercial later. Like those 2-part commercials that they put a commercial between. Hey, welcome back. Let's talk the second half. Because you can't pay attention for more than 30 seconds anymore. Right? Yep. All right. Should look something like this. We have a basic formula. M1 V1 equals M2 V2. What's my M1 and V1? Right. And M1 is 10 molar, good. Okay. And then I have an M2 and a V2. 2.5 molar and 0.5, 0.5, we'll just leave it as 0.5 for now for quick math. So we're solving for the first volume, right? We need to know how much of the original molarity do we need in order to make the second. So V1 equals M2 V2 over M1. 2.5 molar times 0.5 liters divided by 10 molar. So half of 2.5 is going to be 1.25 divided by 10 is 0.125, right? 0.125 liters. So my V1 is 1.25 liters. So describe to me what she needs to do. Yes, ma'am? Okay, so we're going to measure out 0.125 liters of the 10 molar. Okay, we're going to measure out 0.125 liters of the 10 molar, and then we're going to add water to it until we get to a volume of 0.5 liters. And when we fill up the beaker to 0.5 liters, we will have a 2.5 molar solution. Okay, here's the deal. If we have half a liter, and every liter has 2.5 moles, how many moles do we have in it? We have half of this, or 1.25 moles. Right? Because if a half a liter has 2.5, excuse me, let me fix that. I misspoke. If a half a liter has 2.5 mole, then a full liter has double that, right? So 0.5, half a liter has 2.5, a whole liter would be 5.0. So the final molarity is, no, I'm going to take back my take back. I'm sorry about this. Let me go back and state this one more time. This molarity doesn't change. If I had twice as much, the molarity would still be the same, 2.5. If I added more water, I would dilute it. That's why I said if I added it to 1 liter and I had the same amount, I'd have 1.25 molar. But we have right now, take this volume, 0.125 liters of my 10 molar. So I've got a highly concentrated small amount. I'm going to add water to it to increase my volume. When I increase my volume to 0.5 milliliters from 0.125 liters, right? How much water am I adding real quickly? I'm going from 125 milliliters to 500 milliliters. So I'm adding 375 milliliters, or 0.375 liters, right? I'm taking a highly concentrated small amount. I'm adding 375 milliliters, so I've got the same amount of acid in more water, which means I've got the same amount of moles, but my concentration is fewer moles per liter because I've got more volume. And I'm sorry, I cannot take this heat. So it is hot up here. Man, yes, sir. Mm-hmm.
But I wrote M1 as 2.5 instead of M2 as 2.5.
Right, because you look at the problem and figure out, though it came to you first in the problem, they're describing it as being where they want to go, where they want to be the second state, right? So where it says, let me get on the right page, where it says she needs to make, they're talking about the end state.
Like the solution.
Right. The end state, she needs to make this much with this concentration. So that's your M2, V2. And she starts with this much. So they kind of put the word problem in the reverse order.
So M1 is 10.
Right, M1, V1, they're not the first molarity or volume they talk about. It's whenever you actually go to do this, what are you going to start with? And then the M2, V2 is, again, not the second ones that are mentioned in the problem. They're what do you want to end with? So ending with a certain molarity and a certain volume, beginning with a certain molarity and a certain volume, you're going to lack one of those components. Solve for it. And then taking that word problem and looking at it and saying, oh, I see. This is my final state because I'm making that. This is my initial state because this is what I start with, I find. So this has to be my M1. This has to be my M2, V2. So I can solve for the first volume. And then to turn that into what does that mean? If I take a certain volume of a certain concentration, I can then make a certain molarity if I increase that volume to the given volume. And I increase the volume by adding water to it, just diluting it out. And that's how the dilution equation works. If you look at page 334, this relates back to what I was just talking about in terms of using this in stoichiometry. Bottom of 334, we give the equation 2HCl. Okay, now we're going to pretend like this is just another part of the molar bridge. And I'm going to describe it that way to you when we come back tomorrow. That dilution, or molarity specifically, the concentration, molarity is another leg of the molar bridge. Remember we said before we had moles, and then we had mass, and we go from mass to moles by dividing by the molar mass, and then we have Avogadro's number, and we can go from moles to count, or count to moles by either multiplying or dividing by Avogadro's number. We can also figure out moles by knowing volumes given a concentration. And so in the same kind of a way, when we do stoichiometry using concentration, we're actually using moles, but we're doing them indirectly. When we say indirectly, it's kind of like where we talked about 2HCl plus BaOH2, barium hydroxide, reacts to produce barium chloride and water. Okay? Now we said before, if I have 2 moles, if I have 2 moles of hydrochloric acid, and I can produce how many moles of water? And you'd say, well, 2 goes to moles of water, and it's a 2 to 2, which is the same as a 1 to 1, which means, hey, I'm going to get 2. And that makes sense, because it goes from 2 to 2. Okay, 2 to 2. Yep, I see that. Let's suppose instead of 2, I actually only had 1.3. How many moles of water could I make? 1.3, okay? See, you're familiar with that. And then we added to it this idea of, okay, rather than moles, let's say I had grams. And I wanted to go from grams, but I want to do stoichiometry, but I have grams. So I go from grams to moles, and I do that by dividing by the molar mass, right? And then I want to go from moles to grams, and so I'm going to multiply by the molar mass. Okay? Now we're going to add to this idea of molarity. I'm not given grams. Let's suppose that I'm given a volume at a certain molarity.